Welcome back. Today's topic is analog filters and multiplexes. In the last lecture, we have discussed about the basic components of digital relays. We have seen the block diagram and we have observed that there are three important subsystems in a digital relay. The first one is signal conditioning system, and next is conversion subsystem, where analog signal is converted into its digital form, and finally is digital signal processing subsystem, wherein the digital data is processed in order for further analysis. Now, in the signal conditioning system, we have seen that there are four different parts. The first one being the transducers, the second one being the surge protection circuits. We have seen that the transducers help in scaling down the operating values of currents and voltage, and we have seen that surge protection circuits, which are isolation transformers, capacitors, Zener diodes, they will protect the circuit. The remaining two are the filters and analog multiplexers. So in this lecture, we will discuss about the LP filters and also the analog multiplexers. So I hope that by the end of this lecture, you will be able to describe the operation of analog filters and also analog multiplexers and why they are required in digital filters. In digital relays, right? So I'll start with analog filtering techniques. I will give just a basic glimpse about what actually an analog filter is, and then we will move on to analog multiplexing. Now, moving on to the analog filters, normally why filtering is being required? You know that the signals which are obtained from your transducers, they do consist of noise also, which may be because of the transients or any faults in the subsystem. And these noises are to be minimized such that the data can be processed further. So whatever the signal which you receive from the instrument transformers, they are to be filtered. And based upon your digital relay, the amount of filtering will be varying. So normally the filtering, it depends upon the data requirements of a particular digital relay, because some relays they can operate at a wide range of frequencies, but most of the relays they do operate over a limited range of frequency. So whatever the signal which you are getting from your system, that is to be processed before it is converted into digital form. So the best example is, let us suppose normally this is your current signal, which is, let us suppose this is a current signal and it is having a frequency of 50 Hz. That's fine. And now let us suppose if there is any disturbance happening in the system, then there is a chance of the current may increase, right? See, the current magnitude, this is a faulty signal, let us suppose. The current magnitude has increased, but if you carefully see, it is just only a power frequency signal, but just having a different magnitude. So this is okay. Now let us suppose if you do have another signal which is of, let us suppose it is just like this. Now this is also as a part of sinusoidal signal, but the fact is that it is a combination of too many frequencies. If you perform your Fourier analysis, then you can identify that this is also a sinusoidal signal, but a combination of different frequencies. So in order to analyze the signal, we don't need this type of higher order things. So if you perform a frequency based spectrum, if you see it in a frequency based spectrum, we see that it has a good fundamental component, but it is having multiple harmonics. So those harmonics are to be reduced before you convert into digital form. So what we do is nothing but we will try to process it through an LP filter, which basically it removes any higher order frequencies. So any signal, let us suppose, I'm just taking a random one. Don't feel that this is actually a true signal. So let us suppose a signal is like this. Okay. And let us suppose it is a combination of after performing my so it is, so these are of higher order frequencies which are not wanted for me. So I don't need only this fundamental component, which means that this signal which I have obtained, because these type of disturbances are common when we do use different components in the system. So what I should do, I should smoothen this one so that job, so unwanted frequencies will be removed. So the higher order frequencies will be removed. So I may get a signal which is closer to my power frequency, or it may include only sub frequencies of your power frequency. So that job will be taken care by low pass filter. So if you use a low pass filter, the biggest advantage which you do get is nothing but you can get an appropriate signal or accurate, close to accurate signal, which you can analyze then to get the desired data. Right? So what actually an LP filter is? See, you might have gone through your sampling theorem in your signals and systems. You know that as per the sampling theorem statement, any analog signal component above a certain frequency, it is to be attenuated in order to avoid errors in the process of digital signal processing. That is a basic requirement of your sampling theorem, right? So before you process any digital format of a signal, better you take care of removing the unwanted frequencies. So that job, for that job itself, we are employing LP filter. And see, anti-aliasing function, it is to be importantly fulfilled by your filter, such that the cutoff frequency that performs satisfactory signal component rejection above a given frequency. So what I will do is nothing but I will choose a LP filter such that you know that LP filters will be having a cutoff frequency. Below that frequency, they will allow the signals, any signal. Above that, they will not allow any signals. So you might have studied about your LP filter. This is your LP filter. If I take it on a frequency spectrum, see, this is the frequency. This is my magnitude of the signal. Anything below this cutoff frequency is allowed. Anything above this cutoff frequency is not allowed. So earlier signal. See, don't get confused. This has been drawn with respect to time, whereas this is with respect to frequency. So don't get confused. This is a time domain signal. If I process it through some sort of Fourier transforms or things like that, let us suppose if I have got that this particular signal has multiple frequencies. 50 is the fundamental frequency. It is having some 150, 250, and 750, 850, and 1150, 1350, which means that these are higher order harmonics. Okay, this is a 0 fundamental harmonic, or we call it as 1. And this is a third harmonic, this is a fifth harmonic, and this is somewhere a 15th harmonic, and this is 17th harmonic, and I think this is 23, and this is 27. So these harmonics are there in your signal, which you are not able to see. So if I reduce these two things, so this will be just closer to a true actual signal. So this frequencies are to be removed. Okay, so your filter must not allow these frequencies to pass through it. So that is the job which I am doing here. Less than this cutoff frequency, I'll keep the cutoff frequency as 200. So anything less than 200, it will be allowed. Anything greater than 200, it won't be allowed. So this is the selection of cutoff frequency. So this is a time domain signal. This is a frequency domain signal. Don't get confused between these two. Okay. So this is an ideal case, but a practical case will be like this. This is your practical case. You don't get any perfect response like this one. So this is your practical case. Okay. even higher order frequencies also, they will be transmitted actually, but not to this particular extent, partially. As the frequency goes on, then you will get a better response. Okay, so this is the response of an LP filter. If you process your signal through an LP filter, then you can eliminate higher order harmonics, which is required by your sampling theorem. Okay, now when you are doing this for an LP filter, there are some features of LP filter which you are supposed to think when you are selecting a filter. So what are the important characteristics of a filter? You might have studied about these things in your control systems, but let me revise it once again. So our concept is we should take an LP filter, right? Which means a low pass filter. So in electrical terms, in your NT, you might have gone through this LP filter design. An LP filter design is just a circuit which allows only low frequencies but will not allow high frequencies, right? A simple LP filter is an RC circuit. So I'll give you a best example. See, let us suppose if I do have a frequency AC source, I do take a resistor and I do take a capacitor, and this is my output, let us suppose, and this is my input. Okay, so now if you carefully see, the impedance offered by this one is R, whereas the impedance offered by this one is 1 by omega c, isn't it? So whenever you are seeing this system, if you carefully see, at lower frequencies, what happens is, at lower frequencies, now this value is independent of frequency, the impedance offered, whereas this one, since the value is low, so what happens is the impedance offered is high. So the equivalent impedance, you will get some R plus 1 by j omega c, right? This is here. So this is your impedance, right? Sorry, R minus j omega c. So what is the current? V input by R minus 1 by j omega c. And what is my output? Output is nothing but again what I will be getting. This is my current into again my what I should do, right? So if you carefully see what I will be getting here, this is minus j V input by omega c R minus j, right? If I 1 minus j omega c, this is somewhere around like this. Okay, 1 plus, this is my output voltage, V input by 1 plus j omega cr. Now let us suppose if my frequency is low, right? If my frequency is low, then this value will become minimum, isn't it? So what happens? I'll get whatever the input voltage is there, I'll get it as an output voltage. If the frequency is high, so this, as I move on to infinity, omega moves on to infinity, see this value goes to infinity. So anything by infinity is basically 0. So V output becomes 0, right? So this is the concept of low pass filter. As the frequency increases, your output must be 0. As the frequency is low, then your output value must be close to your input value, right? So a simple RC circuit is basically a representation of your low pass filter. So let's get back to our filters. So what are the important characteristics of your filters? Now let us suppose instead of AC source, if I give it a step signal. Okay, so when I give a step signal to my RC circuit, you know what is the response of this one? The capacitor basically it starts as a short circuit and slowly it will develop a voltage, right? So the output voltage will be like this, slowly. This is my output voltage. The input voltage is this one. This is my input voltage, this is my output voltage. See, the time taken to traverse from initial value to final value, it is called as a rise time. Normally, I'll consider from 10% of the initial value, 10% of final value to 90% of the 0.9, 0.1. So 10% to 90%. I'll take this one as rise time. Okay. So overshoot means Actually, this is my, let us suppose this is my desired thing. So if it is going in this fashion, which means that my filter output is exceeding the final value by some value, and this is called as my overshoot. Normally overshoot should be avoided, and then filter must be quick enough, which means the rise time must be very low. And settling time, how much time it is taking for overcoming these oscillations and finally settling down. That is called as a settling time. So rise time, overshoot, and settling time. All these three must be minimum. And unfortunately, they depend upon the time constant of your circuit. That's a different scenario, which you might have studied in your networks, right? So whenever you are selecting a filter, ensure that your rise time and settling time are very minimum, and your overshoot also is very minimum. Okay, so the requirements from an LP filter point of view, you know that rise time, cutoff frequency, overshoot, settling time, all these things, they do play an important role, and they will play an important role in the dynamic response of your digital relay systems also. So select them very wisely. So in particular, when a high-speed decision is required, it is particularly important to ensure that low-pass filter is designed to have a cutoff frequency which gives an overall performance which is not degraded by long filter delays. So ensure that your filter has a very good cutoff frequency and very low delays. Okay. And next thing is